Okay, we'll start with the second lecture, which is essentially a continuation on the DAG-based DLTs. Last lecture we have covered IOTA. Now we proceed to consider to give an overview about other DAG-based systems. So there are three types of DAG-based DLTs. The first type is main chain enhancement. So a lot of DAG-based systems are just trying to improve convergence on the main chain. For example, Ghost does exactly that, right? The Ghost protocol, which we consider in the context of Ethereum, of convergence in Ethereum, does exactly that. Namely, they they use additional blocks, or in the case of DAG-based, it may be additional transactions, which would help compute the weights of the main chain and therefore increase mining utilization. That's the first family. The second family is mostly about sharding. So we shard the large amount of data, we shard the large chain into multiple chains. And then we have several parallel chains. And that situation continues over time. So the parallel chains do not converge. However, they do refer to each other, because there could be cross-chain or cross-shard transactions. So Vita, Nano, and Caper are examples of systems with parallel chains. And in the third category, we have DAG-based systems without predefined structure, like IOTA. In IOTA, the structure, the shape of the DAG is not determined beforehand. It's built on the fly. So one interesting aspect we are going to consider is what kind of knowledge is encapsulated by the DAG. What does a vertex represent? When does a node create vertex? That is, what is the trigger event for vertex creation? Which nodes create vertices? What relation between the vertices and connecting edge represents? So when it comes to edge creation, whenever a new vertex is created, the node creating the vertex also creates backward edges to connect the vertex to existing DAG. So how many of such backward pointers, and what is the way in which the targets of these backward pointers are selected? So let's take a look. Vertex, or let's go over different dimensions and the different choices for each dimension. Regarding the vertex type, there could, like some DAG-based system, maintain transaction and block vertices, which store a single transaction or a set of transactions respectively, along with the references. Other systems build event vertices to record the detection of specific conditions pertaining, for example, to synchronization. Yet more systems use snapshot vertices in order to record, to perform and record a snapshot of the current system state. Some DAGs use voting vertices. So sometimes the consensus algorithm itself creates special vertices, which record the instance of voting, say by a majority or by a number of nodes. Okay, what's the trigger for vertex creation? Transaction arrival. In some DLTs, a vertex is created once a new user-initiated transaction is injected in the system. In some other cases, it's based on POW or proof of stake. By the way, collectively, proof of something is referred to as POX. POX is an abstract reference to proof of work, proof of stake, proof of authority, proof of elapsed time. So it means some mechanism to this end. Proof of something. In a technical jargon, in this area, it's related to as POX. So a trigger for vertex creation can be POX-based. Once a node generates a proof of work of an allocated resource, it would create a new vertex. Next possibility is knowledge-based. A vertex is created once the node acquires knowledge about a certain global condition in the system. Synchronization request. A vertex is created when a node receives a synchronization request from another node in the network. Periodic. In some systems, there are special knowledge consolidation vertices that are created periodically. And finally, pairing. In some DLTs, vertices in a DAG are organized in pairs. For example, a transfer may result in two vertices, one for sending and another for receiving the funds. So far, it's very abstract, but we'll take a look at some systems soon. What are the targets of pointers? What are the potential targets of pointers? It could be all vertices. It could be vertices of particular type out of those types listed previously. In some systems, we pick the heaviest branch and only vertices from that branch. In some systems, we compute clusters of vertices and pick the heaviest clusters. Some systems operate by round, and there are vertices created at each round, right? Like classical BFT protocols, they have rounds, and for each round there are new vertices, and we select vertices of particular round. Sometimes it could be vertices created by a particular node, and there are other cases. Target set restriction, we can create tips paired previous. Now it's getting more interesting. Edge representation. So what is the semantic of an edge? Essentially there are two semantics. One semantic is integrity and the other is validity. Integrity means that if a new vertex points to another vertex, it's like a signature that the older vertex is formed correctly in terms of integrity. And sometimes it conveys some information in terms of validity. Validity means that the previous vertex to which the pointer, to which previous tip, for example, to which the pointer goes, is valid. Valid means no double spending. There is enough funds to do the transaction. There are no conflicts. Okay, validity usually means cons validity. So if you take a look at IOTA, okay, I need one of those graphs, so that would be good enough. So usually the edge signifies validity of the cone. What is a cone? Cone means everything that can be reached from this vertex. So this would be part of the cone, this would be part of the cone, this would be part of the cone, this, and this. That's a cone in a graph. So the validity semantic of an edge usually signifies validity not just of the vertex itself to which the pointer goes, but validity of the entire cone. And then, in addition to validity semantics, an edge may also represent voting semantics. So an edge may, from a later vertex, may indicate that the later vertex votes for an earlier vertex in case of conflicts between different vertices. So here's an example. This is the cone of vertex X and vertex H, right? And in this example, the edge may signify that, for example, vertex F would be competing with okay, that would probably not work. A very good example. Okay, let's consider vertex G, right? It points to vertices D and F. Now it may be the case that vertex E is conflicting with vertex D, okay? So this edge may signify that vertex G votes for vertex D, and the lack of the edge, lack of the path, in fact, from vertex G to vertex E signifies that vertex G doesn't vote for vertex E. And therefore, between the two conflicting vertices, we need to pick, according to G, we need to pick vertex D. And if all other vertices do the same, then this is how we would resolve the conflict. So here you can see a table with different DAG-based systems: Ghost, Inclusive, Spectre, Ghost DAG, DAG-Night, Conflux, Nano, Vita, Graph Chain, Hash Graph, Joint Graph, and Byteball. And here you see classification of different systems according to the vertex type, according to the vertex creation trigger, who creates the vertex. So the options here could be any node or could be committee, and it could be committee node. Any node means that any node can create a vertex without any coordination with other nodes. A committee means that committee is selected and committee members need to coordinate creation of vertices with each other. And the committee vertex means that there is committee, but out of the committee, any member of the committee can autonomously create a vertex without coordinating with other members of the committee. And then you can see that the edge has some validity semantics and some voting semantics, right? For most DAG-based systems, the selection method for the edges is random, or rather first known. Like first known means that, for example, I learn about some vertices first. I learn about 3 vertices, A, B, and C. If I learned about vertices A and B before C, then I would pick edges to A and B if they are all equivalent. And I would not create an edge to C. That's first known. So IOTA is special because it does the random walk. It's the only system which does random walks. So the table analyzes an order of 30 different systems and classifies them from this point of view in terms of the what edges represent and what vertices represent and how vertices are formed. There is also an additional representation pertaining to consensus. So here we have some more basic information about the system. Openness, ordering, and finality. Openness just means if the DAG-based system is permissionless or permissioned. Finality means whether finality is probabilistic, and probabilistic means like in Bitcoin, it never happens, but like we never reach 100% guarantee, but the probability becomes vanishingly small, becomes smaller and smaller with time. So that's probabilistic finality. And deterministic finality is like in BFTs, where there is a point in time where we can say, yes, the transaction is part of the ledger or part of the DAG. And from this point on, the transaction can be considered as final. Now, ordering is another interesting characteristic of DAG-based system. So what does ordering mean? Ordering can be total or partial. Total order means that all transactions in a DAG are eventually converted to some sequential order. Well, that doesn't happen all at once. They may get confirmed even before the total order is introduced, but eventually there would be a total order. At the same time, the partial order means that that total order would never introduce, that there are only some partial dependencies between the transactions, like in IOTA, what we saw in the previous lecture. So it's also interesting to see how conflicts are prevented in different systems. So some systems try to prevent conflicts proactively, while some other systems try to detect conflicts reactively and then try to resolve them later. And if they resolve them, actually in both cases we could use some votes, we could use order between the vertices, or we could use some additional weight-based algorithms. So here you can see a few systems are doing prevention, but actually most systems are doing detection of conflicts. So let's go back to Ghost, which we already know. This is just another illustration of Ghost, right? So this branch is the longest branch, but it's not the heaviest branch. This branch is the heaviest branch. So we already talked about Ghost in the context of Ethereum. However, later there were further development of Ghost. So the main impact of Ghost was on the conflict resolution rule. However, later variations, such as inclusive, did more. So they rewarded creators of blocks in secondary branches. So, for example, in Ethereum, before Ethereum switched to proof of stake, they had the concept of uncles, this concept comes from inclusive. So what are uncles? Uncles are nodes, okay, it's like in the previous slides. nodes which are not, or vertices which are not on the main chain, so they are not on the main chain, but they contribute to the main chain. For example, here the main chain may be this chain, while this one, this node would be an uncle. An uncle is not on the main chain, but its weight contributes to the weight of this node. And this is why this node is selected for the main branch. So the original Ghost protocol only used uncles for the calculation of weights. But later protocols also reward creators of uncle blocks. And another impact of the Ghost protocol, so later variations such as inclusive, merge transactions from secondary branches. So imagine, let's come back here. Let's take a look at this block. So its creator would also be rewarded for pointing out, like the block would be stored in the ledger, and its creator would be rewarded for pointing to the block on the main chain. So that's like an extra incentive to create uncles. But also, this block may include some transactions which are not on the main chain yet. And there are variations of Ghost, again inclusive, which include transactions from uncle blocks which are not represented on the main chain yet, and they merge them with the transactions on the main chain. So in a previous version of Ethereum, Casper, they borrowed the conflict resolution rule from Ghost, and they rewarded creators of block, and they allowed the block to have one main parent on the main chain and two uncles. And it imposed constraints on how the uncles could be chosen. So another question is throughput and scalability. So scalability means number of nodes the system is able to support, while throughput means the transaction rate, number of transactions per second that the system is able to process. And here, each block here represents a different DAG-based system. So as you can see, I mean, the ideal situation, of course, would be here, but most of the systems are not like that. IOTA can have many nodes, like Bitcoin, and it provides, however, its throughput it's higher than that of Bitcoin, but not very significantly higher. And then what we have here, like Caper, it's essentially a sharding system, so it doesn't reach convergence on the main chain. But due to introduction of shards and smart management of shards and smart management of cross-shard transactions, they manage to achieve high throughput. However, they do not scale very well with the number of nodes. So that's another representation of the major trade-off in the design of blockchain systems. So there are quite a few open questions and the research challenges remaining in this domain. DAG-based system is one of the more recent areas of blockchain, and therefore many questions are still unresolved, and a lot of papers are still coming out, research papers in this area. So some examples of open questions and research challenges. How can we support smart contracts based on DAG-based systems? So we can. I mean, there are some systems which definitely support smart contracts, but it's a challenge because ensuring correct state transition is essential for smart contracts, And this requires usually units sorted in a linear sequence for a consistent view. And therefore, only the system designed with linear sorting algorithm has the chance to establish upper layer components such as the smart contract. Next question. Is there a blockchain design that simultaneously scales throughput, storage efficiency, and security? So currently no protocols in the context of DAG blockchain meet all these requirements at the same time. Next question, how can we do snapshot without significant centralization or knowledge consolidation vertices? So knowledge consolidation vertices represent some global conditions that have happened. So it's nice that those conditions can be recorded and represented in the DAG, but of course it inflates the size of the DAG. So, what would be a good trade-off? And in what cases, like currently there is no recipe, no recommendation which would say you need to use knowledge consolidation vertices in those particular cases. Another question, is it better to prevent conflicts or to resolve them reactively? Most of the systems, as we have seen, most of the DAG-based systems resolve conflicts reactively. But is it because it's easier or is it because it's better for the applications? So there are quite a few open questions which remain in these domains. And this is essentially the end of this shorter lecture. I would like to thank you.